All right, we are going to go ahead and do our next example, example 4.8 in your textbook. Okay, so we are looking at a traffic light with some mass, and it's suspended from two wires as shown. And we want to find the tension in each of these wires, neglecting the masses of the wires. Okay, so our first thing would be to identify the forces that are involved here. Okay, so I'm just going to draw on this one. Okay, so I'm going to say there's going to be some kind of weight of the traffic light, right? There's going to be some kind of tension in the wires, okay? And from the pole to the wires, there's going to also be another tension, and the tension will be the same throughout, okay, on this side and then this side. So I will have some tension T1 on this side, and then some tension T2 on this side, and then again my weight due to gravity. Okay, so that's going to be pulling in my Y direction there. Okay, now they went ahead and gave us the angles here, and I'm going to go ahead and call them theta 1 and theta 2, just for convenience. Okay, just when we're getting along through the problem. Okay, so from here, we want to identify our system of interest. Okay, so we want to know the tension in the wires, okay? And since we're given the information about the traffic light, I am going to go ahead and say that this is my system of interest, the traffic light. Okay, so I'm gonna look at T1 and T2 here with these angles, and then my W for weight. Okay, so I'm going to ignore these other two tensions, and then these forces down here I didn't even talk about. So this is my system of interest, and that is what I'm going to be looking at. Okay, so moving on, we can kind of break this down, and I'm going to try to redo my explanation here. Rather than just going off of this. So if I have an X, Y coordinate system here, okay, I'm going to go ahead and draw my tensions. So I've got T1 here, so that's T1. Then I have T2, okay, and my weight here. Okay, I'm going to need to break these down into their components, their X and Y components. So what I will do is I will go ahead and say, here's my T1X component and my T1Y component. Okay, I can do the same thing with T2, T2X, and then my T2Y. Okay, can put little arrows here. This is getting a little bit cluttered, so give me a moment. I will draw something else in a minute here. And then we have our weight, and that is purely in our Y direction. So we don't have to take our X component because it's just our Y. It's just in our Y direction. Okay, so from that, we can now draw a free body diagram. Okay, so I'm going to go ahead and draw that here. And all it is kind of just putting these things on my X and Y coordinates only. It just makes it a little bit easier for us to figure out. Okay, so I have my weight still. Then I have my T1Y. I have my T2Y. And my T1X in this direction. And then my T2X in that direction. Okay, so now this is my free body diagram. Okay, now based on my free body diagram, I'm going to come up with a couple of formulas to find out my net force in each direction. okay? Or not solve my net force, but solve for these tensions, okay? So when I'm looking at, let's say our X first, so I'm looking at my X components, my net force in the X direction would be calculated by adding these two together, okay? And this is where we need to think about or just acknowledge the directions that these tensions are being are in. Okay, so what directions are these tensions in? So this one, this first one, T1 sub X, that is in the negative direction. So when I'm calculating my F net, I'm going to put a negative in front to indicate its direction. Okay, so that's going to be T1X. Okay, and then I will add my T2X. Okay, and that one is actually in the positive direction. So I will leave a plus sign there. Whoops. Accidentally. I was going to write an F, but it's T2X. Okay. So that starts my first equation. Now, my net force is also equal to the mass times acceleration. Okay. But because our system isn't moving when compared to the last question we had, or the last example, we don't have any kind of acceleration. Okay, so our acceleration is actually 0 here, since everything is stationary. Okay, everything is constant. Okay, so there's no velocity or anything. There's no change in distance or no displacement. Okay, so this whole equation is actually equal to 0. Okay, so our F net in the X direction is equal to 0. And so we can look at this now as one equation. So now we have minus T1X plus T2X equals 0. Okay. Or we can rewrite this as T1X equals T2X. Okay. So that is our very first equation. Okay. And we can actually simplify it further. Okay. So because we're looking at the X direction, we can pull these components out. So remember that we had some angles here, theta 1 and theta 2. I'm going to go ahead and add those here, theta 2 and theta 1. Okay. We can now use our trigonometry knowledge to solve for those X and Y components. Okay, so let's look at this real quick. Let me look at T1. Okay, so if I want to know T1X, I am going to say, okay, I need to know the adjacent, right? The adjacent edge. And I know my hypotenuse, T1. I don't know it yet, but that's something I do want to know in the future, right? So I'm going to say that's my hypotenuse. So I will use cosine for my X component here. If I look at my other one, I will get the same thing. If I want to know my X component here, my T2X, that's going to be my adjacent side here. And then I will know my T2 at some point, okay? So that's again going to be cosine. So I'm going to go back down here. And I'm going to now say that T1X, okay, so this here is going to be T1 times cosine of theta 1, okay, equals T2 times cosine of theta 2, okay? So hopefully you guys remember that from when we were doing so many additions of vectors, okay, and how to break those down, okay? All right, so now what I can do is I can solve for either T1 or T2. I'm going to go ahead and solve for T2. So I'm going to get cosine of theta 1 divided by cosine of theta 2 times T1 is going to equal theta or T2. Okay. And I can actually plug this value in, so it's just some constant out front. So my theta 1 is 30 degrees. So cosine of 30. And then my theta 2 was 45 degrees. Okay. So then I would plug that into my calculator. And I will get 1.22 times T1. So this is like an intermittent equation. And so I like to label my equations as I go because it can get kind of confusing. So I'm going to label this 1 prime. You can label it like 1A or something, just so that we know it still came from our first equation, but it's now a little bit different, right? Okay, so that's not really important. It's just something I do. So when you see me do that, you can kind of take it or leave it, I guess. It just helps me keep organized. Okay, so this is one equation that I will be using eventually. Okay, so that was all in my x direction. Now what about my y direction? Okay, so I'm going to go ahead and write over here. Now I'm looking for my f net comma y equation. Okay. So I'm going to start with T1y. So that is a positive value. So I'm going to go ahead and write that here, T1y. My T2y is also positive. So I'm going to add that. My weight is in the negative y direction. So I'm going to call that minus w. Okay. And my net force, since again, there's no acceleration, is going to equal 0 all around. Okay. Okay. So now what I'll do is I'll start plugging in what I can. So let's see. My T1y is going to be represented as T1 times sine theta 1. Remember our trigonometry here, okay? So we got our x value as being the cosine. Now we have to look at our y value. So T1y and T2y, okay? So it's going to be opposite now, opposite over hypotenuse. Same thing here, opposite over hypotenuse. So we're going to use sine. Okay. So we will have T2 sine theta 2. And our weight is going to be calculated as mg. Okay, so that's the weight due to gravity, right? So our mass times g. Okay. So I can start plugging in values. Okay. And notice now that we have a, so this is equation 2. We have this value for T2. I can plug that into this equation as well, okay? So I'm gonna go ahead and put 0 equals T1 times sine of 30 degrees plus, and again, I'm gonna plug in my T2. I'm gonna put a star there and a star here. So I'm gonna plug that in as 1.22 times T1 times sine 45 degrees, okay, minus my mass, which was given in the beginning of the problem as 15 kilograms, okay? And multiply that by G, which is 9.8 meters per second squared, okay? So I'm gonna keep going. All right, so as you can see, I can combine these two numbers since we have a common variable, T1, or a common unknown. Okay, so I'm just gonna write that here. So I'm gonna take the sine theta, or actually let me simplify it a little bit more before doing that. That might make it more complicated. So I'm gonna take sine of 30 degrees. Okay, and that is 0.5. And then again, I have my T1. And then I'm going to take sine of 45 degrees and multiply that by 1.22, which is going to give me 0.87. Okay. Then I'm going to multiply these last two values, 15 times 9.8, and that gives me 147 newtons. Okay. So then I can add those two, and I can actually pull this to the other side. I'm going to go ahead and do that. Okay, so I'm going to have a positive 147 newtons equals T1 times 0.5 plus 0.87. That gives me 1.37. Okay. And then I do a little bit more algebra and solve for T1, and I get 107.3 newtons. Okay, so that is my tension in my first wire. Okay. Now what I'm going to go ahead and do is plug that into this relation here and find my T2 real quick. So 1.22 times 107.3 newtons. And I end up with, 130.9 newtons. And that is my second tension. Okay. So I know that was quite a lot. Hopefully you were able to stick with me through it. If not, of course, you can pause the video, rewind it, go back and see what you missed or got confused on. But hopefully that made some sense. Okay, I tried to go slower with this one. Okay. So again, we found the tension in each of these wires on the left side and on the right side, T1 and T2. Okay. All right, so I have a couple more examples that I'll go through in another video.